of you. I'll pick on you. Have a seat. Here's it. Here's it. And so, and you can see what it looks like. Then the next step the hint was to say, well, that's a map, but you can turn it back into an array by saying to array. So here, oh, then so I can Alt P because Emacs. Alright, so right? So I'm going to look at this array, asking everyone except you. What the heck does this array do? It groups by exponents. So here we have an array, and we have an array of what? An array of pairs. And so here we have the first one here. What do we actually want?
The second element of the pair, and from the second element, the second.
Sum of
coefficients.
So we want these. Okay, how do we get it?
By using the function, by mapping the
Okay, so generally you don't want to do a find as your first strategy. Why not?
Both versus everything.
It's just difficult to think about. So, first, it's more difficult to think about. What's the first planet have?
map.
for each.
Well, actually, why is map better than for each?
But for each you have to use var. I mean, you have to store values.
For each is okay, but it's not as good as map. What's better about map?
Gets the first values by.
But for each also traverses through the values. But what is map always your first approach?
Because map returns a list.
Because map returns a list that you're likely going to need in the next step. Because it's never just one step, or it wouldn't be an exam problem. So you can use, you can either use map or you can use for yield, whatever your preference is. But we're going up here, we can use map. So we're going to map and go ahead, map something. Yeah, type map. Go ahead and type. So what does map take? Okay, why did you take over? So take the inputs to the function.
Same as the array, which is an int.
Just say X.
Double.
Who said not say X? Excellent. So he says, doesn't say X, and that is a very good answer. So the input is a single thing. It is, and we'll see what that single thing is, but let's just call it X right now.
And type is
Okay, so what is X?
it's a pair.
X is a pair, exactly. So, and that means that we're going to have to say X, and then what comes after the X?
Colon. The arrow.
Yeah, you don't have any type, it'll infer the type. If there's any justice, it'll infer the type.
Yeah, but X has to be in parentheses, right?
No, it's just.
It doesn't have to be actually. You could put it, but, so, and now what do we want to do with X? So now we're looking at one of these things, what's in it? It contains an int, and then it contains this array from ints to doubles.
Say X dot underscore 2.
Okay, fine. Let's try it. Okay. Yeah, let's try it. We'll see what happens. Okay, now we have an arrays of pairs.
We just remove the first element of the pair.
Well, we need to figure out how to sum things up, right? So what we've now done is we've removed a bit of complexity, and we didn't actually lose anything. Did we lose something?
Yes, the first element.
I think we kind of wanted the first element, right?
Yes.
So we wanted the first element. So let's see, what can we do with these? So what we want is we want to sum up the 3 and the -3.
So again do a math.
Okay, give it a try. So odd P gets you back to what you want. Okay, now make another map. Okay, actually, good suggestion, right? Because then we don't get confused with all the x's.
Again map on 1.
What is y now?
It's an array. Array of pairs, so you want to map on each pair.
Okay. So you want to map? Go ahead, type map.
Can't you use the underscore?
You could, but and that's what I would do. But this is a simple, straightforward way of doing it. So what do you map Zeta? What are we trying to do?
Pairs 1, 2.0.
Right.
And then there's 2.0 from it, so C dot underscore 2.
Right.
But then moving outline. Some minutes of basically you want to definitely do it as 3.0
Okay, dot underscore 2. Let's give it a try. Z dot underscore 2.
map will remove underscore will remove elements.
Okay.
You lost.
Yeah, I know, perfection has eluded us, but that's okay, because we're learning. The coefficient of y, how do I sum them?
Sum on each.
Right, so,
Again, get the each element and then dot sum, map and then sum.
yeah, okay. Try it, Alt P. Sorry, it's image, you have to move the cursor back here to Alt P.
All.
Okay, I think you had cognitive overload. Why did you go next?
So you want to map a function which takes this element q, and then just say q dot sum.
Okay.
Now you filter it.
Yes, so now we're very good. Now we just need to figure out where did we lose the coefficients?
For the first map.
To dot map.
So over here,
In the first map. The map before
so
that.
over here we actually have twice, right? So we need to make a decision which one we want to keep.
Yeah. Maybe the first one from map.
You want to keep the original ones.
Yeah.
Okay. No, I'm kind of fast with the mouse. I want to go out.
I just, it's possible, I guess, but let's for contrarian spirit, let's try to see whether we can't capture them here. So here we have, this thing is these arrays of pairs,
Um,
and,
yeah. How do I go up, sir? How do I use the
I'll keep.
how do I use the mouse page down?
What do you want to do?
I want to basically move this guy up.
Page up?
Okay. So after that we lost it, right? After here.
Yes?
No, into a really had it.
Is this I'm to array, we did have it.
Yeah.
Okay, yeah. After the first map we lost it.
Yeah.
Yes or no, I mean, here they're still in here. So we still have these twos here.
Right. Okay. So here in the second map, we could keep the first element also,
Right.
right?
See, over here, each of these is an array of pairs, right?
Right.
And what we want is we want to have that first thing. Well, I see why you're saying it's harder to pick it out here. Okay, I'll buy that. So over here, we had it,
There.
not nice. So over here, we had it as the first coordinate, and then we had it followed by the array. So, okay, I'm buying your fact that it's easier to tease it out here. So over here,
X under it should be saying X underscore 1 comma.
we'll see. Okay, can you scroll down a little bit? If over here,
The first
we
map.
are,
There.
if we,
Take a pair as a return value.
okay, over here, keep the x dot 1
Right.
down here.
So that's rest2 dot map. Okay.
So do Alt P a few times until we get it. Alt P. That's not a command line? Hit enter. That's okay. Do Alt P a couple of times.
Here we want to keep x dot y.
Okay. Give me a pair.
X dot 1 comma.
Yes, and now on this guy here, on the x dot underscore 2, that one we now want to do some interesting mapping.
Correct.
Dot map.
Dot map.
And now just to do anything at all, just give us the, just give us the second component here.
So underscore dot map. I'm just writing the z
Okay,
part.
over.
So z dot underscore 2. That right?
Well, we'll find out.
No.
It's not a member of int, comma, double. Let's go to the previous one, we'll find out where. So it's this map that it didn't like.
Correct.
Yeah, in second map, capture it as some variable and just sum that.
Here?
Should do it.
No, it's this one here that it didn't like.
Yeah.
Okay. So
This one here is an array of pairs, and now you still need to get the second one, so do it underscore 2.
okay. Should I just write another variable here?
Just do it underscore dot underscore 2. Dot underscore 2.
Okay.
Okay, now try it.
No.
I mean, now I actually have to think. I hate that when that happens.
Yeah.
Why don't you give variables that
Yeah.
like somewhere?
So let's say this was y.
Yeah.
What was y?
Y dot underscore. So you are basically mapping on an array of pairs.
Correct.
Correct. So x dot underscore 2 was an array.
And this is an array of
It
pairs.
was an array.
Correct.
Map.
Now you want to get each pair from the array.
I'm going to get the second one. Let's get the second one first. We're doing too much in one. Do it underscore dot underscore 2. Okay, hit enter.
Okay.
Uh-huh.
This is the same thing.
No, it's not.
One.
Because now we keep on going here. So now we have this array here.
Mm.
So this array is an array. This one is easy to sum on. Just do Alt P.
Okay.
And now back here, so put in a sum.
Map 2 dot sum. Right?
Yes.
Okay.
And now we get rid of the.
Filter.
Okay, go for it.
So this gives me an array where I have to filter underscore dot 2.
Underscore 2.
Yeah. Underscore dot 2.
No.
Oh, 2.
Because this is the variable and this is the, it's a crummy notation.
So underscore dot 2 not equal to.
Try it.
Is it just not equal to?
Just keep on going, give it a try. If it's wrong, there's no penalty.
Yeah, that's it.
No, that's not the syntax.
Well, because you missed,
Not equal to is right.
no, there's too many parentheses. So erase the parentheses, erase the other one, and retype it. And now you see how it is.
Just 1, right. So I got 2 minus 1, yeah.
Okay. Yeah.
Can you display res2, res2 again?
Okay.
Go ahead, that's what RES too.
No, I actually wanted to see the function. And,
RES 2 was obtained.
yeah.
That was the hint that was in the exam to put out group by
And then
and by 2 array.
Can you just go?
That's 0 dot group by underscore 1 dot 2 array.
So what's required for these things is the willingness to run these experiments and to learn from the mistakes. And people really do this.
Yeah, we try a lot.
No, that's why when I looked at the transcript, and so I actually showed Gudersky the transcript, and he said, they aren't even trying. Because no one got to the point where everyone got to the point where one saw this and maybe one extra step. And so it had never occurred to the poor man that people wouldn't try 3 or 4 other steps.
So I actually finished this problem, except I didn't do the filter again, so I totally forgotten. But like all this whole process, like I did that, you can look at my transcript, it's like super long. It took me like forever, you know? Like, I didn't have any time for the rest of the day.
So I guess then we're going to have to figure out,
Yeah, I'm not.
at the end of the day, I make it one step easier and you get to be a step faster. Yeah. And so maybe one of the things is that whenever there is some kind of a puzzle on the news group, you can see that there's like 20 people trying to come up with the shortest solution to that puzzle, and that's how they practice these kinds of things. They just have had the experience of running 100 programs like that, and which is a good exercise. So what I've noticed that a whole bunch of people have similar trouble with Scheme, where like the most basic things, is not very natural, and I'm just going to come up with a bunch of suggested exercises for people to try, so that we all get better at this. And I think that's why the students that I had before, they just had run many more of these so that they could do it quickly. Now, as an interesting and amusing exercise, do this in Java. I should make that as a sign, but do it in Java. Actually do it. You know you can do it, but actually do it.
Can't we do another language?
What's that? Or what? C++. I don't know. What do you normally use? Well, in Ruby you can do this, right? You can solve it the same way. But do it in Java or C++, and you see that it's actually just as painful. Because to collect all of these things and to do the sums and stuff. But I think it's not really what Gudersky's theory was. It was too abstract. That maybe these lists, because I didn't dare count that I was using arrays instead of lists. So those are all back from the transcript because it gives me an idea of how hard this really is. People ask me in the office about some good questions about the first homework, which is probably the hardest. So I send the deadline for it, but I really want that everyone gets the thing to a successful conclusion. So, and so much people said they had never seen this in their undergraduate programming language courses, and never had an undergraduate programming language course. So I need to give a little bit of more background on how the basic interpretation step works. So the concept number 1 is this environment. Yeah?
I have one basic question.
Yeah?
What is the difference between evaluating and interpreting?
Nothing really.
Because in the first problem, you said that amazingly enough the code can evaluate itself.
Yes.
That is fine. And then in the last sentence you said, show that your interpreter can interpret itself.
Oh, I mean the same thing. The evaluator can evaluate itself.
Okay. So, what are some?
So when you
Yes.
say eval and something, it first goes and gets the bindings, creates the bindings, gets them, and then evaluates them.
Well, yes.
What happens when we say eval?
So let's step a step back. So you have this function in Scheme or in Rapid that can evaluate an expression in this mini Rapid. The function that you're writing, you're not just writing in Rapid, but you're actually writing it in mini Rapid, right? that means that it should be able to evaluate itself, because it can evaluate any mini bracket statement. And what happens when it evaluates itself? The output has to be another eval function. It does much slower eval function. And so we can see that by having that function consume what the my eval consumes, namely some coded list. And if it still works, it'll run much. Or you don't notice it runs much slower, but it'll run slower. Then that's a powerful proof that you probably did it right. So having this universal function that can evaluate any expression, and because it's written in the same language as the target language, the amazing thing is it can evaluate itself. It's not good for anything. I mean, it's just a slower way of doing it. It's so in 252 we deal with these Turing machines that can interpret a Turing machine, and they use that to build up all sorts of results about what's not computable. But a Turing machine is not very much. It's not a very nice piece of equipment, right? It's just this weird tape and it goes left and right, and it's totally unintuitive. And naturally, I mean, have you ever built a Turing machine that consumes itself? It's really tedious. But here in 50, 60 lines of scheme, you can write this thing that does it. And you see it right in front of your very eyes, and now there's a mess of left and right moves. So we've got this kind of self-evaluating thing, which is more sophisticated. Let's just understand that the basic way one writes an interpreter, a scheme interpreter. So the first concept is that you have this environment which is a list of negative value pairs. So you would have that x is bound to 3. We don't have 3 in our subset. Did you notice that we have no numbers in our subset? You can fake numbers actually, but we're not doing that. I was hoping we'd get to that by the end of the course, maybe not. But you can think of faking numbers as, if you need to fake the number 3, you could make a list of 3 x's. We have symbols. And in addition, that would become concatenation. So let's use numbers for right now. And then y might be bound to 4, and then f might be bound to lambda xy plus xy. So that consists of 3 things: x, y, and f bound to different things. What can something be bound to? There's different possibilities. So you can be I'll put in parentheses because in our mini language that's not going to be the case. It can be a lambda, of course, a function. What else could it be?
Can be primitive.
It could be a primitive. Absolutely. Such as in this case we would consider plus maybe a primitive, but in a mini racket there's only 9 primitives. And what else can it be? Yeah. Exactly. Or
If condition.
that's a list. Everything's a list.
Code.
A quote. Because a quote is kind of special. So you have the possibility of a number in mini racket.
What do you precisely mean by quote in this?
It's something that has the form Q-U-O-T-E followed by something. It's special.
What would they do from quote and this kind of thing?
We have to check the code first. So when you have something that looks like a list, you have to first check that it's a code. Because code things are special.
So even for actual racket, code is not a function, it's the special thing.
It's a macro. But it gets special treatment.
So when you say eval quote, it doesn't mean.
So no, eval strips away one level of coding. So what's eval of a list?
A list with each member evaluating.
Takes the first element and that's the.
Yeah, we got the list. That makes sense.
Right?
Eval to each. No. First to
Almost. So that's not quite right. So it takes the first thing in the list, and that's the function, and it applies that to the rest of the list.
So if the list just consists of numbers, the first is not a function.
Right. So that's
It gives a procedure after.
1, 2, 3.
Yeah.
That's the end.
Yeah.
So if we evaluate plus 1, 2, 3, then it will be 1 plus.
This one will be fine. Right? So it's an error if the first thing is not a function. You don't have to worry about errors. You can assume that all the code that you get is syntactically correct. No error handling. Right? Of course, one could add on error handling to this thing, but we simply have the keyboard mounted to hollow plastic here. This guy. So we assume that the first one. You have the rest of the list, and you have to implement a play as well, right?
Yeah.
And this is almost right, except there's another step that you have to do, is you have to evaluate. Because there might be symbols. It might say plus A, B, in which case you need to look up what A and B are. Or it might be F, A, B, in which case you need to look up what F is as well.
So when you say f is a function, how do you actually store that value?
Yeah, how is that
Especially
defined?
Okay. So there's a many factor to define something, and that's with left. So if you run a program that does anything non-trivial, is likely going to start out with left rec. And so it might say F. We can't do much here. So that's just to do something silly. Okay. And then I might define A as yeah. And I could say in this environment evaluate f of A. Well, that's actually a bad example because it's not going to work. Okay, this will work. So now I'm going to evaluate this whole thing in a diagram of my choice, and let's say I start with the empty environment. So this is a typical program, the way that would look. So we missed a few cases on the previous slide with what eval has to do with. One of the things is a letter. So what does eval do in a letter? needs to, on these guys here, make pairs F eval of the right-hand side, you know, the second thing here, and A eval on the right-hand side.
And the eval of the right hand side doesn't work.
So when you do eval of the right hand side for f, and it goes and tries to evaluate first of x.
No. So now the question is, what is eval of a lambda?
Right. Right. So you have to create it such a way that
Okay, what is eval of a lambda?
Just a list with
What is eval of a lambda?
if it is a function,
Yeah,
function which
it already is a function. The lambda is already a function. What's eval of a lambda?
So it's not a function.
It's already a function. What's eval of a lambda?
So isn't the combine the function to something?
What is eval of the lambda?
It's not lambda itself, that's what it
It's exactly the lambda itself.
exactly. It's a function.
It's the function. It's the same function. It's itself.
That's what it
Okay,
says.
well, you said it's a function. A function of anything, right?
It's a function.
Yeah, so it's itself. So when you, so let's see what happens here. So we're calling eval on this thing. It's going to return itself. And I'm just representing it as the lambda list. It's a list that starts off with a 6-letter word.
Can we,
Yeah.
in this, can we use like an actual thing that works, that this is giving an error? That
It can't give an error because what you're having is you're having a done all list. You're not asking Scheme to interpret anything. It's a list that starts out with LAMBDA.
it says bad syntax.
If you get to the point where it says bad syntax, you're not quoting it enough. The entire computation is a computation of abstract lists. So from the point of view, the Racket has no idea that you're building another Racket interpreter. If it already knew, it would have stopped you. Right? But it has no way of knowing. It thinks that you're manipulating lists. It's kind of, if you remember the lab with the derivatives, you didn't actually compute any mathematical derivatives, right? You just tossed around symbols. You just operated abstractly on lists of x's and y's and numbers. And it's the same thing here. You're having a list that just happens to contain things like LAMBDA.
so you mean to say there is no binding happening when we are evaluating a lambda?
When you see a list that starts out with the 6-letter
Yeah.
and lambda, you draw it on. So in email it says if the first thing of the thing is lambda,
just return.
then it's itself. He said if the first thing is letter, then I respond to this complicated action that I'm in the middle of describing. If the first thing of the list is something that you can find in one of these atomic ones, and it's one of those 6 or 7 cases, you just call, and you already have the code for that because it's boring. There must be code that I gave you that says if there is one of these exactly, then you just execute on the host language. And if it is, there's a couple of other situations. When it's quote, you strip off the quote. And if it is a list, then you have to do that I showed in the previous slide. Then you have to call apply. So if there's a list where the first one is not one of the special forms, then you have to evaluate all of the components, apply the first to the rest.
So then it will be some primitives, right? In that list. The first
Well, not going to. I think I know your question. He's leaving it this time. Alright, so last 2 years I used eval. Well, in other words, there is no such thing as eval. Eval only works with an environment. In which environment do I evaluate these right-hand side?
And the one which got
Yeah, the
nine.
one that got casting,
Yeah.
right? So Meaning when I come from the outside world, I have no particular knowledge about what any symbols mean. And I can come in here. I'm going to show you the environment down here. So, and that's the environment that it now goes on to evaluate this thing. So now, when it sees an effect, it builds up a new environment out of this thing. In that environment, it evaluates the body. So now it recursively calls eval of the body with this environment. That's what left reference is. Let's assume that the body is a little bit simpler. Right now the body was f of a. So suppose the body had actually been a. How do we evaluate a?
Let the binding. Oh, I see.
Maybe you have to get the binding out of the environment and return it.
That's what is the Maya organ.
So, and how do you know to do that? You have to see that A is a symbol. So is there something in the code that says if it's a symbol, then just fish it out?
If the expression is not a list,
Okay.
then it comes to the Maya get, which looks in the environment and looks for the binding.
I see. All right. So in that case, it just what if it doesn't find it in that list?
It just
It returns itself.
Oh, I see. So it's possible that that's the pathway through which the lambdas return themselves. I don't know that. I don't know that. So
You said when it is a lambda, you have to return itself.
yes.
And there is ... for us to fill in. So I thought we have to make a line return and
Maybe.
return.
I'm sure there's plenty of stuff to fill in. So we evaluate the body inside this environment. Now, this is something that is already kind of a good exercise to just write the code for it, because when you think about, there is a bit of a technical difficulty in making this list here and calling eval on this thing, and then you want to call eval again. So that's how the heck do you make this list? Because here we have to kind of loop over this thing. No one likes to loop. Do we have map?
Yes.
And so you will definitely want to use map to iterate over this thing and build this thing.
Right. The rest of the list to the eval function.
Now I was asking, you had in letter, the second of letter is this list of pairs.
Right.
Now you want to transform that list of pairs into this environment. And so how do you do that? And so for that you will surely need to call some map that does this evaluation. Okay, now the next question that people have is how do these function applications work? So now we're back to the point that I think we were when I said let's draw the line. How do function applications work? So here I have f. I look up f in the environment, and what do I get?
the list, a lambda.
I get a lambda.
Yeah.
So I'm now applying a lambda. So I have apply of a lambda x body to what? To A. What's A?
The list spread.
The list spread. And actually, I think there's an extra list in here because I'm applying it to the tail. I'm applying it to the rest.
Right. And you actually calling my map on the rest. So what happened?
Well, I did call on the rest. I must have called my at one point or another. I must have evaluated these hookups.
Right.
Right. So I added on the previous line where I said evaluate everything. Evaluate the first and evaluate the rest. Now, then what's the better strategy? Maybe you first evaluate everything and then split it into the first and the rest. Maybe you evaluate the first and then separately you evaluate the rest in map. I haven't thought about it before. So when we evaluated F, the evaluation of F made it look up in the table and gave me the lambda. When we evaluated A, it gave me this thing. And I need those things to apply. What does apply get? Apply gets two parts. It gets the lambda, and this is going to be a lambda. Well, almost. It could be a primitive, right? But I'm not sure if we even got to this point if it was a primitive. I don't think we ever got, if we got to this point, well, it's possible that it's a primitive, right? Because what if
You got to check in there. First of the list is lambda, LMDDA.
yes, I think so.
Then only you basically.
I think you got it right. Because it's possible that over here I could have bound F to like my map. My map is a valid symbol. Evaluates to itself. And so it's in that case, I would have to check for the lambda. So let's say it's a lambda. So that's the interesting case. So I have here are the lambda, and here I have the args. A list of args. And I can assume that the list of args is exactly as long as the list of parameters. Now what?
Add this parameters and its args to the environment.
That's right. So here I have an environment. So I add to another pair that says X is bound to Fred. And now I have a bigger environment. This whole thing. Yeah?
And then eval the bot lambda.
And then the eval in that.
Now there's one question, sir. The recursive thing.
Yes.
So what if my F had something after, like in the body,
We'll come to the recursive stuff in a minute. I just want to get everyone to appreciate the basic setup where we don't have to.
So this first binding, the evaluating RHS to F and RHS to A, this happened in my eval itself.
In metric.
In metric code, the code corresponding to the metric.
This one, yes.
Right. And the next binding, which is actually mapping the variables to the function, that happens in apply. Spread.
Okay, so it's actually one more step that you're doing, that eval of metric calls eval of the body in the augmented environment. Eval of the body, because the body happens to be a function application, calls apply. And then apply is kind of a self-standing thing. Apply matches up the parameters with the arguments and then calls eval. So let's get another parameter that I've forgotten here where it gets the initial environment.
And no, it doesn't get actually. Apply just gets proc and args. So we thought we just get the environment which,
Because it's like you're getting it globally,
I see.
so we could just use
so we are just mutating global
No,
environment.
it's we're homing in on the truth here. So what she said is that apply does not get an environment passed in as a parameter. It just gets the procedure and the arguments. And so I actually lied about what is a procedure.
It comes with its own environment.
Procedure comes with its own environment because
It's a local environment.
it's a closure. Every closure comes with its own environment, right? So a procedure comes with its own environment, and so that's the one thing I said the land evaluates to itself. And that's not entirely true.
So it evaluates to itself by adding an environment.
So let's find out what a procedure is. Yes. So the procedure actually has two parts to it. It has the lambda, and it has some environment. And the environment is a list of pairs. And so that's actually how I do represent a procedure. So that means that when I eval a lambda expression, something that looks like this, and I have an environment, then the result is that pair. So I'm trying to make sense of what does this lambda actually mean. And that's what eval does. But it's actually given, it has an environment that presumably tells me what all of the surrounding variables mean. And so that in that, I do that.
So my question
Yeah.
is, suppose all of this is inside the letrec, like
Yes.
the previous thing you had, your letrec,
Yes.
then F and then lambda, and then A and then a port Fred, okay? So letrec will initially create a new environment with dummy bindings.
Okay, yes, so I think now we're almost ready to approach the line.
Okay.
Okay, I just want to, if you look at the whole case, let's say that I have let me use numbers, it's easier to visualize it with numbers. And let's say I can do addition, right? X. And you'll see them in Y next to letters. So,
You can do that.
and then inside here I compute f of 9. So, in the scope of the first letter right here, it gives me a term that says A is 5. And I go down here, and I need to evaluate what is F. F is this thing here, where A is 5. So the evaluate even on this thing here gives me that pair lambda x plus ax, where A is 5. I'll just make my table like this.
So it just go inside and see what all binds.
No,
No?
it doesn't go inside.
Okay.
It simply copies this thing. You don't have to see that there is an A inside here.
It just gives
Yeah,
it.
You just retain the whole body as it is.
Mm.
You don't try to make any sense out of it, but you just simply just use the previous environment and say that's the environment in which this lambda has been typically played. That's the environment that provides all of the global variables, all of the previous variables. Yeah, you don't know what's that. That's important to understand. So if this thing contained like a C and the C was not defined, then this would blow up. We're not doing anything. And in fact, you can see that scheme does the same thing. If you want to define a function that says lambda x plus cx, and c was nowhere defined, the definition will go right through. But when you try to use the function, then you will get there. So that's what eval does. It produces this pair. And then later when we call it plan on this pair, we don't need an environment to do the next eval in because we already have one. We take the environment that the thing came with, and inside that environment we add our parameter argument bindings. And again, we add the parameter argument bindings, we don't bother to look inside the body at all. We simply make a newer environment that has the parameter argument bindings, and inside that we recursively call eval and let the chips fall as they may. So there's no particular intelligence to it. And that's kind of the, if you think about it, that's kind of the amazing thing that eval calls, recursively calls eval when you have a letrec, eval calls apply, which calls eval when you have a lambda, and that's all evaluation is. There's nothing to evaluation at all except it is to interpret, it's to interpret it as a network. accept maximum parameters and arguments, and containing some atomic things like cars and cutters, the plus. These basic atomic operations. There's nothing else built in at all. That's all it ever does. So, what do you want to know about this? So I'm going to do with factorial because it's an easy example just to see. So let's say we have left rec factorial lambda and then let's say we already have, if it's greater than 0, that this is a primitive that we have. I know we don't have it, but I'll show us with this example and then we'll see that example. What is fat minus n1 and another one. And inside the document we want to compute fat. Right, so use the factorial function that says fat is now equal to this funny lambda that says if n is greater than 0, multiply fat of n minus 1 with n, otherwise return 1. That's the definition of factorial, end of the left rec definitions, and inside that left rec I want to compute factor. And so I want to evaluate the whole thing. Now let's see what this evaluation, even the left rec, says add this stuff to the symbol table, and in that environment, execute factor. So now we do factor. What is fact? Fact is two things. It is the lambda expression together with an environment that binds names to values. Now let's see, what is this environment? So we're now going to this lambda expression here. And now we're looking for free variables. Now greater, star, minus, 0 and 1 we assume are somehow predefined, so they're not free variables. N is it free?
No, it's not.
It's a parameter. Fat?
It has a dummy.
It's free. It is free inside this expression. It's undefined inside this expression. And so that's our problem right now. That because when it calls itself, it will look itself up in the other environment, the empty environment that came in, and it would find itself and it wouldn't compile. And so here's where we have to do this curious trick. We have to say, well, actually, fat is bound to something. And what is it bound to? The lambda. It's bound to. To this thing. So we have a circular data structure. Of course, this list here, when I write it as a list with parentheses, is actually a reference to a list. And so this thing is going to be another reference to the same list. That's why I have to establish the circular data structure. So that when the evaluation time comes along, let's follow it through. So we're now evaluating fat of 3. How do we evaluate fat of 3? We're making a new environment in which we start out with this environment. We're putting in the 3. So now we have, we don't actually need this part here. And so now in the new environment, fat is this thing here. We have n equals 3. In this environment, we now evaluate the expression on the right. In this environment, n is 3, all of these things are known, fat is known, it's that thing. And it comes along, and then eventually we'll simplify the column. So, we're going as long as we can make it so that fat is defined in an environment in which fat is itself. Now, unfortunately, that has to be a two-step process because we can't do everything at once. So in step number 1, we set fat to dummy. And then when we're done, when we have thing, if it's where we have it popped out, then we have to change, we have to modify the binding from coming to itself. And that's where we need that what is it, mod or set, what? So this where we need that magic of soft set component. So this choice change, we have to do this. The recursive function that kind of well, because many does loops. Notice that so far there are no looping constructs in this mini language. Recursion is equivalent to loops. You can express any recursion with a loop and the other way around. Yeah?
So is an environment, like, how exactly do we make that? Is it a list or?
It's just the pairs.
Is it a list?
You use this, there's a bunch of predefined functions, convenient functions that let you look up.
Those are all the MySoc.
Yes, exactly.
Yeah.
Yes. So I think you do those with your bare hands too, but I found at some point it's kind of doesn't show anything extra. And we're just adding 30 lines of boring code. So I'm just taking those primitives. So on the command just to see what they do. That's what there's a long set of pairs. Is maintaining a list of pairs. Because there's so ubiquitous in scheme programming. Just anytime you need to have a hash table or something, you instead use a list of pairs. And you just use those. So what the set does is it uses a more potent set primitive to actually home in on that pair, on that second part of the pair and set it. You could write it with your bare hands. I just thought it was plausible that you could stop right there. Actually, if you want to have some quick and dirty exercise, there's your exercise. Implement those functions with the more primitive function. Great exercise. So it's very good to implement recursion. You need to do this one pure thing. Everything else that we've done was completely functional. We can't modify anything. Eval calls apply, apply calls eval calls eval, and then calls apply. It's just the one function call, not calling another. Yeah?
So in your my app and my second and all the functions that you've defined, there is again a lambda there.
So there are a couple of utility functions which are there.
I'm sure it's a good question. I just can't even begin to visualize it right now.
In the code,
MySoc get as a lambda.
so all those functions you have used lambda to define them. How does it work?
I was one line of abstraction off because I didn't remember the detail. So I did actually show you how to implement these with mcard with mclear. That was nice. You're welcome.
Thank you.
So you didn't have to do these tedious applications.
So our question is,
Yeah.
actually we are defining the code for lambda in the myeval,
Yeah.
but in these utility functions you have already used lambda to define them as functions.
It's inside the left part. Yeah.
No, this thing is taken care by the actual
Lambda?
Okay, so so here's we do this on the interpretation on two levels, right? And the first level here is we're just having the ordinary eval, the scheme eval, interpret this thing.
Right.
The scheme eval, once it unfolds this thing, perfectly well knows how to deal with lambda.
Okay.
It's its own lambda.
Correct.
On the second level, you're feeding this thing into itself. But you have written code that knows that if you find an LAMBDA, what to do with it.
Yeah.
And so your code will actually go in there and say, whenever it sees my socket, it will look up in its symbol table that this is actually this thing.
Because we don't add that in it, it's already there.
So, but I would say, first of all, don't think about it. first of all, get it to work, and then you can start thinking about that. Because I think that just really confuses the issue. So I've given you these helper languages. You just take the position that, for whatever cruel reasons, I'm limiting you to only using this small subset. But I've given you those, and so you can use those. By the way, I didn't give you cond, right, which is responsible for this ridiculous little thing.
So, yeah, I have this question in mind applied.
Yeah.
Other than primitives, I will have lambda and
So here it says if it's a list, then
Oh, that's all the
you do
non-list.
all the primitive procs. And over here, it says if it's not one of them, we return proc.
No, the primitive part is all comes under the not list. Else, if proc is not a list, then all these primitive things come. The dot is.
Here's the part where you have to do the work. You're absolutely
So
right.
we'll check that for lambda. And what else could be there?
Oh, the plan. It could be a symbol, and then you have to look it up. But we might argue that it's our problem. We can do with what we want. I think you can argue that apply. It has been looked up already.
yes, because that you're doing there before, unlike SI.
I do indeed. Look at this.
Yeah.
I gave you so much help. Look at this. Yes. So here, that's exactly right. So
Yeah, so basically if it's primitive, you're not giving list, you're basically.
So I'm looking at. So you can assume it must be a lambda.
Yeah, only lambda.
Yes, it must be a lambda. There's no other possibility. Because the eval of something that's valid at that spot is either a lambda or a primitive. Eval has finished, because here you see it finished. Yeah.
Can you get my map in a list? No.
What's that?
Can you get my map and in a list? My
It can't get my map. It could get whatever my map evaluates to, which is a lambda. So the rule of the game is that when you call my apply, that the first thing must be a lambda or a primitive. And you can totally run it, otherwise it's a syntax error. And so now you only need to deal with the lambda. That part is actually easy. All you have to do is map up the parameters of the arguments and call eval. 2 lines of code.
So the deadline is extended for this question alone?
No, we'll extend it for all of them.